So they are protesting or?
It is my great pleasure to introduce you Professor Felix Aharonian. It's my great pleasure because I think it's a great speaker for a colloquium of the ICCUB, but also because he has been working with us, with University of Barcelona, with ICCUB, with our group, High Energy Astrophysics group, led by José María Paredes, since already almost 20 years. And therefore I'm really happy that he's giving this colloquium. Felix Aharonian, he's a very well-known scientist. He has a great record on high-energy astrophysics. He has been working in different fields in a very long career, in cosmology, in nuclear astrophysics, and in different aspects of high-energy astrophysics like observations and theory. He got his PhD from the Moscow Physics and Engineering Institute in 1979. During that time, working in Moscow, he was collaborating with very high-level scientists like Seldovich, also with a younger Sunyaev and other very highly reputed people. Then in 1979, he moved back to Armenia. Felix is from Armenia. He went to Yerevan, and he was leading their group on very high-energy astrophysics, basically during the whole 80s. Very powerful group, actually. And in the beginning of the 90s, he went to work with Jim Cronin, who is a Nobel Prize winner in Chicago for 1 year and a half. And then in the 92, he moved to Heidelberg, where he has been leading till nowadays very well-reputed, very well-known group on high-energy astrophysics, more theory-oriented, but also with a strong link to observations, very high-energy observations, related to HESS, for instance. And he has, since 2006, he's a full professor in the Dublin Institute for Advanced Studies. And, so you know his, now his records, you know his career. I think, well, it's a moment to let him to talk. Thank you very much, Felix.
Okay. So thank you, Valentin, for introduction. And it's a great pleasure to be here in Barcelona. I'm often here. And in part, we have to. So it's great pleasure to be here, and in particular to meet my Catalan colleagues and friends and colleagues. With, as Valentin said, we are collaborating over almost 20 years, and on different topics, in particular some topics which have relation to this talk. So you see the title is, there is one keyword, is extreme. We often use word extreme, something remarkable, powerful, exotic. But in this case, the extreme is a really keyword in a sense that even it could have a more precise scientific or mathematical definition. It really implies extreme. Extreme means just everything. I'm going to talk about the machines, devices in nature, which operate at the extreme efficiency, 100% efficiency, which predicted by theory. So it cannot be more, but is not sufficiently less, almost the same level. It is a big surprise because typically when we deal with theory, in practice, everything is much lower efficiency. And here we have a different problem. Difficult to understand how these machines produced in nature could operate at such effective level. So these are not astrophysical objects. These are objects related to astrophysical objects, like on all scales, by the way, from the compact objects like neutron star pulsars to black holes and or to large cosmological structures like clusters of galaxies. So surprisingly, everywhere, not all particle accelerators, which you call cosmic ray factories or factories of relativistic plasma, operate at such level. But some of them operating like extreme accelerators. And so the idea of this talk to demonstrate how we can conclude that they are operating like extreme accelerators, and at the same time, what are astrophysical implications. So, of course, the topic relates to the high energy astrophysics. High energy means just high energy. And just to say that universe itself is a high energy phenomenon. So, at least in the framework of the Big Bang theory. And we don't have any other theory. So, the universe started as a high energy phenomenon. Its birth was incredibly energetic event. And quite a long time, of course, much shorter than the age of the universe. Universe it was a hot soap consisting of relativistic particles and radiation. And now, the 2.7 K, which is the relic of the hot universe, it was extremely hot. It's cold at the level of the 10⁻³ of the energy of visible light. So now universe is cold, but it contains so-called cosmic ray factories, producers of relativistic plasma. In other words, in a more simple language, these are particle accelerators, and which produced, we could say, the fourth substance of the visible universe. So which are the first three substances? Of course, it's matter, it's radiation, and magnetic, or better to say, electromagnetic fields. So we have this relativistic non-thermal plasma, and it plays a great role, this substance, in many astrophysical environments, in particular the pressure, which is a very important aspect of this, could be comparable, even exceeds, in some cases, the pressure of turbulent plasma, turbulent gas, pressure of the thermal gas, pressure of magnetic field, pressure of radiation. So comparable, or it could even exceed. So you could imagine how dynamically important are cosmic rays. And the relatively low energy cosmic rays are very important for such a classical aspects of astronomy, like formation of the stars. For formation of new stars, you need the ionization, and it is believed that cosmic rays could be one of the most likely substances which produce this ionization. And without ionization, it would be impossible to form the stars. So, but these are low energies. I'm going to talk something much higher energies. So here are these cosmic ray factories. Of course, the first you see the LHC. It is the Large Hadronic Collider. It is probably the most sophisticated, most complex, and probably also most expensive the device produced by mankind. I mean, we don't have anything more sophisticated, but still it is a quite not so efficient device. So we need very much to have it to understand the physics of interaction of the elementary particles, but we put a lot of energy to get these particles. Even you see how just precisely is. But in nature, in the chaotic efficiency, I don't remember exactly, it should be something like 10⁻⁵. It means just you put energy 10 to 5 times more to get these energetic particles. In nature, in completely chaotic environments, you could get efficiency close to 100%. And so the first is the what we know also as non-thermal particles are relativistic. These are solar flares, and that, you know, this ejection of the matter is accompanied by there's a magnetic field, turbulent plasma, shock waves, also relativistic particles. But this also is a quite small scale phenomenon, I mean, compared to others. But then, surprisingly, and I'll try to show, of course, very briefly, that we see the particle acceleration in many, many type of objects. Neutron stars, black holes, gamma ray bursts, supernova remnants, more extended ones, like pulsar nebulae, starburst galaxies, AGN jets, cluster galaxies. So astronomers immediately could recognize, they could ask, so what remains else? I mean, actually, all these objects are accelerating particles, and some of them are accelerating with the efficiency, what I said, that was called extreme accelerators. And what is interesting, some news, it appears that the stars, massive stars, are also extremely effective accelerators, and then they compete even supernova remnants. I'll tell about that historically we relate cosmic rays to supernova remnant events, so supernova remnants, supernova events. But now it could be just, we should a bit change the paradigm. It could be just the massive stars are even more responsible for highest energy cosmic rays than supernova remnant. So something like dead stars versus young stars. So it could be just young stars still are more important than dead stars, opposite to the standard paradigm of cosmic rays. Okay, so how we know about these accelerators? Using the so-called messengers. The messengers are the cosmic rays themselves, so these relativistic particles are coming to us, and that was we got the name cosmic rays, historical, maybe not the best name, but that is historically called cosmic rays. And cosmic rays have been discovered more than 100 years ago, 2012. They are relatively low energy particles, but formally it starts history for cosmic rays 2012, for which Victor Hess got the Nobel Prize. And for many cosmic ray physicists, there's a community, big community called cosmic ray physics community. For them, the cosmic rays are just most important aspect of that. But in fact, because you see the cosmic rays, so locally we detect them, but it is a quite difficult task. If you detect the cosmic rays, they are coming, the charged particles, cosmic rays are protons, nuclei, electrons, all are charged particles. And they are moving in intergalactic, interstellar magnetic fields. They lose the information about the primary direction. So we see kind of, again, soup, which is cooked for over many years. Many years means for galactics, for example, cosmic rays, for 10 to 7 years to 10 million years. They are cooked by many different sources, and they are together, we detect them, and from the smell of this soup, and smell has a meaning, it's just a spectrum, energy spectrum, anisotropy, chemical composition, we should decide the origin of these cosmic rays. Of course, it's very not so easy thing to do. Just we have to have imagination, good knowledge, but still, it's just very integrated information. If you want to understand the sources, you need really neutral particles, neutral messengers, which will bring direct information about the physics, about the conditions in these objects. And these are, of course, photons, first of all, these radio, optical, X-ray, of course, gamma rays, because gamma rays are high energy. So in order to have high energy photon, you need at least to have even higher energy charged particles. Neutrinos, of course. Gravitational waves, maybe in direct way. It could be just these explosive events when accelerated particles accompanied by production of gravitational waves. And you know, one of these events of gravitational waves was coincided with the gamma ray burst, and the gamma ray burst phenomenon is a non-thermal phenomenon. So there's an acceleration of the particles. So that could be all connected, and now it's very fashionable in the interdisciplinary, how to say, the field or discipline is called multi-messenger, multi-wavelength astronomy. It's used very often, sometimes exaggerated, but this is really, we are in the era of multi-wavelength, the multi-wavelength people used even 20, 30 years ago. That was, in that sense, is exaggerated. I mean, of course, if you want to understand comprehensively the phenomena, you have to study at all wavelengths, not just simply one wavelength. So, and the multi-messenger now comes. Typically, these are neutrinos. This is just one more information. I'll mention a bit briefly about that. So I think I will not have much time. Maybe I'll later make some comments, interesting comments, what means high energy, what means non-thermal. But let me just to move, as I said about multi-wavelength, there's an excellent example is the Crab Nebula. Crab Nebula is a very unique source on the sky. Is a superstar. Superstar means a like object. It's just a lot of discoveries have been done from these objects. So it is powered by neutron star. It is a pulsar. We see the pulsations, but the energy of the rotational energy of this object is a fastly rotating. It's converted first to electromagnetic energy, and then converted to electron-positron pairs, ultra-relativistic, and then these electron-positron pairs terminate, they produce shocks, shock-accelerated particles, relativistic electrons, which produce in a broadband the non-thermal emission from the synchrotron emission, synchrotron radiation to ultra-energy gamma rays. And here you can see the electromagnetic, the frequencies extends from 10 to 10. In fact, 10 to 9 is a gigahertz. We detect even 100 megahertz we detect from the crab. So 10 to 8 up to 10 to 28, 10 to 29. So the huge decades, the range of decades we detect emission, and it consists of two parts. Is a synchrotron part, electrons produce synchrotron emission, and the second high energy part, the same electrons produce the inverse Compton emission. This is more energetic, but it does mean that the electrons which produce more energetic gamma rays are most energetic. Actually, most energetic ones which are produce synchrotron emission, which extends up to 100 MeV, 1 GeV, and these are 1 PeV electrons. 1 PeV means 10 to 15 eV. So then 10 to 15 eV, this is a just signature of extreme accelerator. I'll talk about that a bit later, just a bit of brief introduction, because it's incredible how you could accelerate particles to 10 to 15 eV. Thanks. So how you could accelerate 10 to 15 eV at the presence of magnetic field, we have something like 100 microgauss. It means you have to accelerate these particles at the limit of acceleration rate, which is allowed by theory, and theory is very solid theory, classical electrodynamics, nothing else. I'm not talking about a lot of dissipative processes, I mean the instabilities, plasma. So it seems nothing works. Everything goes at the rate which tells us the classical electrodynamics cannot be faster, and only in that case you can get 1 PeV electrons, and we see these 1 PeV electrons in this object. So this is a classical extreme accelerator. So a few words about high-energy astrophysics. So all these objects are part of the discipline is called high-energy astrophysics. Now is a bit more fashionable, using sometimes astroparticle physics, but typically this is within this discipline. Now, major objective of the high-energy astrophysics is not only the non-thermal astrophysics. Some X-ray physicists also, they call part of this community high-energy astrophysics. But typically, the major objective, of course, is non-thermal phenomena, study of this phenomena in the most energetic violent forms. And many topics are related in one way or another to exploration of the nature's perfectly designed machines. It's really perfectly designed. Designed, just you could not complain any aspect of these machines. I mean, they operate absolute efficiency. And that is a big surprise because that happens in very chaotic the environment. It's not just no one sits and then designs the machine. So that is really, it is a big surprise. You could imagine why stars are rotating, like neutron stars. Also is incredible, but still, all we could imagine all these things. But how you produce from the thermal plasma, you accelerate particles, and with such a efficiency, when it should be a lot of the problems of acceleration, but it seems we don't. They are not realized. Otherwise, you'll not see such energetic particles. Now, okay, coming to cosmic rays, it's coming to the cosmic rays. This is extends from sub-GeV energies to 10 to 20. Again, the huge. They look to huge energies. They look like a nice power law, but it's not the case. It's just the presentation. If you go to you multiply to the E2 square or 2.5, you could see structures. In fact, now, last 2-3 years were kind of revolution in cosmic ray studies. A lot of interesting results are coming at low energies, like IMS. And we see even more structures here, much more structures. But I'm going to talk about two structures. It's called the knee, it's called the ankle. So knee, it is the end of almost the end of the spectrum of the galactic, the part of the galactic cosmic rays. And ankle is the end of the part of the extragalactic cosmic rays. So it is believed that below 10 to 15, all cosmic rays have galactic origin. Above 10 to 18, they have extragalactic origin. I think there's almost no doubt about these two statements. What is not clear between 10 to 15 and 10 to 18. Now, but even if you assume that 10 to 15 is galactic, is a headache to understand how particles could be accelerated in galactic objects up to 10 to 15 eV. So you need extreme accelerators to get them. And extremely well-designed accelerators. What concerns these 10 to 20 eV particles, then really absolute extreme accelerators you need. There's no other way to get them if they are not absolute accelerators. So just only the fact that you have 10 to 20, you could conclude that they are extreme accelerators. So a few words what means the origin of the cosmic rays. In many reviews, even for decades, many books have been written, many reviews, and always you see this standard statement, origin of cosmic rays remains a mystery. So that is a bit very standard, but I think it's kind of exaggeration. We know a lot of the cosmic rays, in fact. It's really exaggeration. Also depends what do you mean on the origin of the cosmic rays. For cosmic ray community, to know which sources contribute to the cosmic rays which we see. So, and there's, for over 70 years, maybe more, was some consensus. These are low energies are contributed by supernova remnants for a good reason, and 10 to 20 could be active galactic nuclei, so general picture. But this is interesting, of course, which object contribute, but this is not the most important aspect of the field. So, so under the cosmic rays, we understand it has two meanings. One is the locally detected non-thermal particles, so which are main contributors. But there's a much more fundamental aspect of the field is the fourth substance of the visible universe. I already mentioned there are three substances we know: matter, radiation, electromagnetic fields. And this is a relativistic plasma, nonthermal relativistic plasma, cosmic rays. It's a more fundamental issue. So origin of the cosmic rays within cosmic ray community is reduced to this identification of the major contributors. It's very interesting. So what is the origin of we call the local fog, what we detect? Very interesting, but okay. Very interesting. But another thing is just this, what is the physics of these accelerators that at least from the point of physicists is more interesting, but also it's good to say supernova remnants contribute. You like to identify, to see really supernova remnants identify accelerators so that you cannot do with cosmic rays themselves. You need neutral messengers which will bring you information. So you need astronomical tools. You need to localize on the sky these objects, and you can do that only using astronomical information. So gamma ray astronomy, gamma rays have, of course, played a key role in these studies. And gamma rays themselves also is a saying gamma rays as a part of the electromagnetic spectrum is not sufficient, because gamma rays occupy, you can see from 0.1 MeV is 10 to 5 electron volts. Optical visible light is approximately 1 electron volt. And it goes up to 10 to 14, 10 to 15. So it's huge. Many decades, more than 10 decades, while electromagnetic visible light we see is not even 1 decade. It's just simply half decade. It's just something between 300 nanometers to 600 nanometers. And then, of course, now we deal with these broadband gamma rays. And of course, it's much more, it's very exciting, to deal with this. And these gamma rays also have completely different origin, like low energy gamma rays, MEV. They are gamma ray lines produced in nuclear reactions, while 100 TeV gamma rays characterize these interactions of proton-proton interactions. So it's completely different physics, different radiation process. So now gamma ray is called last window, and you see this is not just only one window, it's just what that means, last window. But we could say the window is opened now at MEV, GV, TeV bands. So low energy and high energy, these two bands, belongs to the so-called space-based astronomy. All gamma rays have very small mean free path, like X-rays, and they are absorbed in the atmosphere. They cannot reach us. So in order to detect them, you have your detectors to put above atmosphere, and that is satellites. And that is the space-based astronomy. But if you have very energetic gamma rays, they are absorbed, but they produce electron-positron pairs, which produce again gamma rays, and then again absorbed, so cascade develops. And then for sufficiently high energy primary gamma rays, we detect the products of these primary gamma rays. So it's possible to use ground-based detectors. And this will be two types. One is when these secondary electrons produce Cherenkov light. They are sufficiently fast. If you have the electrons with energy more than 300 MeV, then they produce Cherenkov light. You detect Cherenkov light, so you have your own detector. The atmosphere serves as a like detector. You produce Cherenkov light and detect, or if they are even more energetic, you could detect the secondary particles of cascade particles. So there is no much time to go details, but I just want to say that we have this situation now with very high energy gamma rays detected by ground-based detectors. And that was until some 20 years ago, still was considered like kind of science. It was not taken very seriously. But over the last 20 years, a real revolution happened in the field. Then the so-called Cherenkov imaging telescope rays have been designed and proposed, and then immediately start to detect many very high energy gamma rays. So now we have the ground-based astronomy in this energy band, zero point 0.1 TeV, 100 TeV. Just again, 0.1 TeV is 10 to 12 electron volts, so 10 to 12 times more than optical photon. And we detect the photon by photon, and even more than 100 TeV. And another interesting, just to imagine what is that, 1 TeV is approximately 1 arc. So 1 TeV electron is 1 arc energy, contains 1 arc energy. Now, the field is not over. There is a great potential for ground-based astronomy. You could go down to 10 GeV, 1 GeV if you use huge dishes, optical dishes. And there's a technology, and you have to invest a lot of money to go to so-called 0.1 PV or PV astronomy range. And that is also coming, or actually is already here. I'll mention at the very end. So gamma ray astronomy could cover huge interval of energy with very, very good performance. I mean, like angular resolution, few arc minutes. You could not surprise astronomers with few arc minutes, but ground-based astronomy, for example, have few degrees at low energies and 0.1 degree at highest energies. So energy resolution is perfect, is about 10 to 20%. And if you have sufficient photon statistics, then you could do morphology, you could do, if you use astronomical language, morphology, spectrometry, timing, and that is happening, that has happened, and that is the secret of this success of ground-based astronomy. So all these ingredients like angular resolution, energy resolution, photon statistics are in one place. So it is unexpected success was, of course, but at least from the point of view of performance, that we could predict that what was unexpected, that nature produces so many very high energy gamma ray sources. And very high energy gamma ray source means accelerators. I mean, first you have to accelerate particles, then to produce gamma rays. So very briefly about the future. So this is the Fermi satellite. Probably you heard about that. Many extremely successful satellite is with 1 square meter area. It detects directly gamma rays. It seems at this moment this field is saturated. We need a much bigger instruments, but it's not so easy to do that. I mean, at least there are some ideas, not clear what could happen. For the Cherenkov telescope, this one of the telescope is located in La Palma, and this group in Barcelona is directly involved in this experiment. It's called MAGIC telescope, is this. And so that is, there's no saturation, it's just question of the funding, I mean, investment. If you have more money, you could put more of telescope, you could cover more area, you'll have more photon statistics. And particle detectors, some interesting things have been happening over the last few years from the instrument called HAWK. It detects just particles, not Cherenkov light. A lot of interesting things have been reported. shock waves, they terminalize. If you have shock waves like 2,000 kilometers per second, after termination, it produces for you plasma with temperatures which produce thermal X-rays. Here, it seems we have the same situation. Unexpectedly so many TV gamma rays, however, the situation is different. It's one thing to terminate shock waves, or you flow the plasma on the black hole. Another thing, how you get from the thermal plasma to accelerate into TV energies. It is extremely difficult. It is possible. Extremely difficult and almost unbelievable what concerns these extreme accelerators. Not all of them are extreme accelerators, some of them are extreme accelerators. So, how it works? You just detect gamma rays in the sky. So you have an image, like astronomical instruments. Typical for X-ray astronomers, these are much smaller images. But radio astronomers, they have larger images. So you get gamma rays from different parts. You can go together and you see such a structure. This is the supernova remnant, and this is the shell. As I said, over decades, all astronomers, physicists, believe that the cosmic ray accelerated in the supernova remnants. It is true. They have to interact with gamma rays, and you see exactly what you would expect. So from the shell. By the way, what we first time showed this picture at the conference, in 2004 or 5, and we were talking about, and a lot of people didn't realize, we asked them, so, but where are your detection images, gamma ray images? They thought we were showing X-ray images. They didn't believe that we could show that gamma ray images, because they are very, very similar. So they are the shell structure. Another type of object, so pulsar nebulae, and they have a different morphology, and these guys are useful for electrons with cosmic rays, these more cosmic rays. But so it is really good. It's proved that they are straight particles. But it's not the end of the story. You'll see that there are only one of these possible accelerators. Then again, how it works, we measure the spectrum. So this is the gamma ray spectrum. There are two possible ways to interpret data. One that is an atomic interaction of accelerated protons produce the gamma rays, or inverse quantum electrons produce gamma rays due to inverse quantum effect. And then you could derive the spectrum of the protons and the electrons, and then you see what you see. So in this object, from this picture, protons are distributed here in the shell supernova remnant, and they have a spectrum like this. Everything sounds extremely interesting, nice, except for one problem. I mean, there's a break of 10 to 14 eV, and we need to have them to go to up to 10 to 15 eV, and this is the best one. You know, we don't have another source which goes to 10 to 14 eV, so they break earlier, and while we're expecting that we should go to 10 to 15. So I'm just coming now. The point is that since this is I told you about the keyboard extreme, just again to inexpensive other nice pictures to show you to say what means extreme accelerators. So these machines were working with efficiency close to 100% efficiency. So, and then with efficiency, we understand two different things. One, you convert available energy in any form, rotational of the plasma, or thermal energy to non-thermal energy. And that would happen with 100%. So in supernova remnant, it is about 20 to 50%. The mechanical energy of the shocks goes to acceleration of the particles. In pulsar nebulae, almost 100%. More than 70%, like this Nebula, the rotational energy ends up with relativistic electrons. And as I said, it is not just one process. You have rotational energy. you accelerate particles, and then you radiate. So you see about 5, 6 stages, and efficiency is about 10%. At the end up, you end up with 10% or 1%. And imagine if the stages is very efficient, each stage will be 50% still, you'll not get this number. So just imagine what is happening there. So, but this is not the first one. The second one, how you could accelerate particles to highest possible energies. That is even more serious problem. Because we know the maximum possible acceleration. Acceleration happens in electric fields. It could be chaotic electric fields, it could be regular electric fields. And we know the rate how it should be done. And then you calculate that rate. Even you forget about the degradation of energy of electrons because of energy losses, you get incredible numbers, I mean incredible requirements. And so again, that is close to 100%. So they are extremely two cells. Now, I'll start with this. How much more? Okay, I'll start with this. I mentioned this 10 to 20 EV proton. They have been discovered by the way some 40 years ago. It's not new. And that time, people realized how difficult to accelerate this particles 10 to 20 EV. And there's a very famous, extremely modest person, it's not very well known in the world community, but extremely famous with his contribution in several areas. So he just realized that he just tried to put the, based on the requirement that the larval radius should, the relation between magnetic field and the size of the object, based on the relation, that condition, that the size of this should be larger than larval radius. Just very simple. And then produce this maybe small map is just like this here. It's a review in 1984, is the size, is the magnetic field, and he realized that is written here is very nice, it's very clear sentences he has. Clearly, very few sides remain as possibilities for 10 to 20. Either one wants highly condensed objects with huge magnetic field or extended objects. So in either case, very high speeds are required. We also realized that we need very high speed. The reason is the following. So if I convert now the new version, there are a lot of versions of so-called Hillas plot, and Hillas plot, we will see that we will satisfy this larval radius size condition in this plot magnetic field of the size. Are AGN, galactic clusters, and it is a bit old. There are also GRBs now, so not many objects. So this is what I was telling you about the acceleration rate. So acceleration rate is simply ELG divided to EBC. We write often, but it's not EBC. Magnetic field does accelerate particles. You need electric field. So then is this factor eta with the ratio of the magnetic field of project of electric field to magnetic field. And in electrodynamics, this is proportional to the speed. So in other words, you need large magnetic field, electric field, and it's becoming electric field comparable to magnetic field only in the relativistic outflows, where you have a flow with speed of light. So that is the very interesting. So that was written in Hillas. I was talking to a lot of people. They didn't realize that how smart was says I didn't need the speed. So and now we have, if you don't have a speed, you should compensate for large magnetic field or large size. And we know a typical size for magnetic field is classical astronomical objects. We could say, okay, no, galactic galaxies do not have size. Clusters of galaxies maybe, but for this requirement. But satisfying this requirement still not the green light. It's just to satisfy the requirement, but still how you accelerate the particles is a big issue. Now, just saying that this is the assumption that large radius is equal to the size is not innocent assumption. It implies that this beta parameter should be close to 1. And it could be 1 if electric field is comparable to magnetic field, and that is, which is the classical electrodynamics is very strict, very classical discipline. You cannot jump. It's maximum you can do that. And it appears now, just from the fact, 20 in particles, you say all they have to calculate why with such a speed. No, but there are some other issues. For electrons, of course, you'll be violated because there are energy losses you have to take into account. But even for protons, if you go to such high energies, you start mechanisms which typically we ignore. Synchrone emission of protons. Typically we think the protons are very heavy particles, so synchrone emission we ignore the protons. But you go to such high energies in magnetic fields, they become very important. And another very famous scientist in the 60s mentioned that, I mean, they are not writing papers after this conference proceeding by Greisen that say, oh, synchrone radiation could be a problem. And then you say, okay, I will avoid synchrone radiation. How will you do that? You assume the particles are moving along the magnetic field trajectories. It's possible. Still, if you have current magnetic field, you have another radiation, it's called curvature radiation, just because it's not linear. So, if you don't have to avoid fully losses, then you have to have a linear spread. It's just absolute linear spread, which is almost impossible. So the curvature of this object is about the size of the object. Like neutron stars or pulsars is 10 to 6, 10 to 7, 10 to 8. In other words, if you could already discuss all these things, and compare, you arrive to a very interesting conclusion. There are only two types of objects which could satisfy. These are AGN, small jet, and large-scale jets. So, large-scale jet is a 100 kiloparsec jet which is going from quasars very far to objects. Or very powerful AGN quasars which are very compact, powered by a black hole in both cases. And these are remaining one of the likely candidates. You see, we don't see particles from them, we did not see, but it's a possibility. And what was in recent years very interesting thing, these objects start to show very unusual behavior. So, very short variability. Variability is shorter than the gravitational radius over the sea. So that even you invoke relativistic effect, Doppler effect, it's very difficult to explain this short variability. It's just you think the minimum time scale is the gravitational radius divided by the speed of light. Some objects, and this was this object detected by they show variability at the level of minutes, while the gravitational radius over the sea is 10 times more. So there are tricks, there are ways to find it, but as I said, tricks. It's very, very difficult to explain that. Another one, it appears that these objects are super elliptical. So for astronomers, it's very unusual to say super elliptical. They could accept super elliptical maybe twice, 2 times more, or 5 times more. Maybe for students, what is the elliptical luminosity? If you put a lot of matter on the black hole, they radiate, radiation becomes so high, luminosity, and the pressure, the radiation pressure stops further fall of the matter on the black hole. And that is, it depends only on one parameter, mass of the black These guys now show more than 10 times, 100 times. But this still is okay. You don't violate basic rules because it means that energy which goes to the black hole in the accretion doesn't go to the thermal emission as astronomers, X-ray astronomers are. Most energy goes to accretion of the particles. And that means that what you remember I was saying how huge energy should go to accretion particles. So radiation is much less under radiation. It's, so you don't have this problem to stop the falling plasma. At the same time, huge amount of plasma goes from the black hole. Somehow, somewhere, with some data we don't know exactly, we have some guesses, some theories, and they are abstracted to such energies. Just, I make things very simple. I mean, not wrong, not correct, but sometimes I'm simplifying things, but just to show that, indicate the problem. Problem is very serious for that to me. Now I just go, yes, and the indicator of this radiation could be all extreme accelerators are characterized by classical emission, 6-photron emission, the tip of 6-photron emission. For electrons, it is about 100 eV. For protons, 200 GeV, and with the Doppler boosting could be high. It could be just this radiation in TV gamma is a 6-photron radiation of the protons. So that could be the best indicator of extreme accelerators. So just go now very quickly about the galactic cosmic rays. I think I don't have time to go too much about the paradigm of the cosmic rays. Just mention one thing. I already told you that just mention the famous paper by Zwicky and Bade. Zwicky was a famous astronomer who did a lot of bright ideas, and most of them have been realized. And one of them is this one. So in one short paper for two pages paper, they put several famous things. They predicted the neutron star in the Crown Nebula. They predicted that supernova remnants. They are thinking this supernova remnant is possible nebula, but nevertheless, in general, it should be operating with these kinds of objects. And that was, it is really unbelievable how correctly they, 70 years ago, estimate also cosmic ray density. Everything was just really, it's very, very nice paper. And there they concluded that since that time on, we were beginning that having thinking that the supernova remnants are made contributors. And then when we saw the supernova remnant, I showed you the spectrum, I showed you this image, spectrum, so you should be very happy. I mean, that happened. But in fact, not. In fact, not. In fact, we see now travel with supernova remnants. So they don't go 10 to 15. Maybe for low energies they could produce. Most likely they are still may contribute to low energies, but for high energies we need something else. Again, I'll show you. Is the best example, even that as well beyond 10 to 14. We need something to come here. And this object we put pevatrons, galactic pevatrons. So, and the theory also has a problem, and theoreticians, some theoreticians indicated the problem of supernova remnants. They say they are good objects, but not the best ones, like Cesarsky-Lagash many years ago. It was ignored that for a long time, this problem. And when Tony Bell found a way to get this 10 to 15 theoretically, so by enhancing magnetic field by cosmic rays. So sorry, I'm too fast now. I know that probably is not difficult to understand, but just take the problem. It was a problem. There was a solution to the problem, but not a real solution. The problem suffers a lot, and now experiments also do not confirm that. So what you should do, you should relax and try to find maybe some other objects. So one was a few years ago, and yeah, supernova remnants actually show very small spectra. So I'll finish very soon, just to tell you that as I said, we should relax and go to some other objects. And one object was found in galactic center. not directly. It's a diffuse gamma radiation, which, based on the morphology means image of the picture. And the spectra look like that the cosmic rays are producing gamma rays, and they originate from the central black hole in our galaxy. Ironically, black hole in our galaxy was introduced in order just to get more power, but it's the black hole in our galaxy is just tiny, not tiny, it's big, it's solar masses, but luminosity is very big. So in the past it could be high luminosity, so it was some speculation that maybe galactic center, the black hole, is responsible for that. However, I recently found some other objects, and these are young stellar clusters. So there are three famous young stellar clusters in the galactic central region, and now it's doubt maybe these are young stellar clusters. And then you'll remember that even in that paper, which I said, Dr. Zarkis and colleagues, are mentioning these massive stars. Because you remember I was talking about the speed of the bulk motion. So they have the wings stellar, similar to shock waves in supernova remnants, but they have other advantages. So they have indicated potential sources, and now we see experimentally, observationally, we see this interesting. So large stellar clusters remain the second, potentially, and maybe more likely than supernova remnants, candidates to explain galactic cosmic rays. And if they are, still they have to work as extreme accelerators. So we don't have a room to reduce the efficiencies. So given the speed of the wings and the magnetic field. Now, I didn't mention about CRAB, but CRAB is an extreme accelerator for electrons. Let me just finish, a few words also. When you about binaries, I mean, the group in Barcelona has been working for many years in that. So these binaries now have to show their strength. Energy of the binaries goes up to 35, 40 TeV or even more. And what is very strange here, that was paper by Waters recently, and these are the electrons, most likely. It's very difficult to imagine that would be protons, so it should be energy losses. And in binary systems, there are huge reservoir of protons will degrade the energy of electrons. So it's very difficult to imagine how they could go to some energies at the conditions when they are losing energy on the vessel. But this is they go. So they are also extreme accelerators. Now, we'll just finish the next generation. So its success was great. So kind of, you could say, its generation was revolutionary. We ground-based instruments. There are several telescopes in La Palma, in the United States, and it was natural that now we move to another major, so CTA, so Chernobyl telescope array, which is a quite brute force approach. I mean, you just put more telescopes, and then you have a more larger area, and that also creates a lot of interest. So people are emphasizing moving more sources. It's important, but it could be even more interesting. I mean, they could investigate the details of the existing sources with great details, and that could be much more exciting, actually. Because, as I said, everything what we go to understand the sources is a surprise. And this is not exaggerated, and really it's very, very difficult to understand how it could be produced within existence. And the last thing what I should tell you is the now new instrument appeared, is operating on 50% in China, to some extent unexpectedly. And here the performance is amazing. I mean, they get a sensitivity. You could see what is the scale size, like underground neon detectors, more than 1,000, each of them 40. It's almost difficult to imagine in these scales. But they did that, built that for So it's just only started. I cannot put the names of the sources, objects, but something is new is coming, and this white kind of instrument is pretty much random, right? So one could say that revolution continues. I mean, that was again unexpected. Some very will be many interesting results over next year. So just instead of summary, I just show you that maybe I don't know that I'm just saying just put all potential sources of pulsar particles, and then all they are fit. So they are missing only Young-ray bursts. Now there are also Young-ray bursts. So all of them accelerate particles very effectively, and some of them more than effectively just at the close to 100% efficiency, which is called extreme accelerators. So this is very interesting material, not only for astrophysicists, but maybe even more to physicists now to understand what is going there. What is important, this is not science fiction, we detect these objects, and we are puzzled, but there are, of course, explanations that are quite new. So, and there is very interesting material to start to understand, invoking a lot of knowledge in hydrodynamics, in plasma physics, nuclear physics, particle physics. So all interpretation of these objects need a really very broad knowledge in different fields of physics. So it's really multidisciplinary. Very exciting for theory, but what about analogy? Experimental data are coming. It's provided by the experimental data. That makes this field very feasible, reliable, and we could predict with really very future, at least for the next 20 years, what will happen in the future. Okay, thank you for that.
Thank you very much, Felix. We have time for questions, so please feel free to raise your hand and feel free to ask.
So, Felix, you said that we should somehow relax and accept all the ideas. We have been focusing for many decades on supernova remnants. So what are the sources that you think are the most promising sources? And massive stars is now.
Massive stars is the colliding with the massive stars. And massive stars, most of them are in the binary systems. And they are two colliding waves. Each will be 3,000, 5,000 kilometers, and together will be 10,000 almost, right? So it's much more than supernova remnants. And the supernova is a big problem, so-called astrophysics go away. We don't have the astrophysics. Tell you that wasn't created by the astrophysics. So this is extremely promising, and energetically, they're almost like total energy that winds is about 200 like supernovae kinetic energy. Yeah, I think I myself was just very happy and was almost sure that it's a central black hole. But now what we see with these young stellar clusters, it could be. That was I'm saying that the young stars versus dead stars. So that looks like that stars play an amazing role. Yeah. And another thing now I still notice Lahasu. It means you need not even proton, you need superproton. You have to go 10 times. And then that's the only pulsars. But then pulsars should not have protons. It should not have protons. But we say now should not. But maybe we need to say maybe we have straight protons. So that would be very interesting outcome of this talk. So that I think we should be really open-minded now. Absolutely open-minded, and then try to take seriously theory, by the way. Very often in these interpretations, theories just a bit easily let assume contains so object, like I say, in this color velocity galactic center, is G1.9. It's 100 years old, but even it happened in one first year, right? It is in the galactic center, it's very massive pulsar. So if they are straight there and they escape, they still should be within 100 years, they should not go too far. And then our upper limits are earlier and makes cosmic rays of right there. So that is a good example, at least for this distinction of random. It's not the case. And there is a nice thing also with Casset. Casset also is inside a big, huge complex with 26-fold massive. So for 300 years, there are no upper limits, but now to the Hasselblad. So for 300 years, with even very fast diffusion, they could not go far away. And since they are inside with a massive complex, then you could have upper limits and a big portion could be rejected. But another point is just really theory. Now, if we know our compensating problem, but before, we often ignore the problems. So finally, that's this string stability and accepted by people who did that, like one of them. So they are also correct with all of this.
Questions, comments? That was too long. Questions, comments? Okay. If not, well, I think that we can thank Felix again for